All right. Good morning, everybody. Hope your break was fantastic. I know mine was, and I hope you are rested. Um, Hope everyone's well wherever you are, whether you're on campus or back home, wherever home is for you. So today, gonna go over, well, recap a few things we've already talked about in order to kind of lead into a couple things today, specifically speakers, amplifiers, and metering. Uh, like the different types of meters that you would see on equipment, whether it's outboard equipment or inside your digital workstation like Pro Tools or Logic or whatever you're using. So let's just jump into it. Uh, so we already know how we perceive sound, what sound is. Sound is changes in air pressure, right? You have a sound source. It moves air molecules and creates pressure waves, areas of high pressure, high pressure, low pressure in this wave form that eventually hits our ears, which then vibrates our eardrum, which transfers that energy from pressure into an electrical response that our brain then perceives as sound, right? So we know that. Uh, we know that microphones work in basically the exact same way that our ears do, right? Sound waves or changes in air pressure hit a diaphragm in a microphone that transfers that energy in one of two ways, either with dynamic microphones, right? It's electromagnetic induction, where the the capsule is then vibrating around a magnetic field. It disturbs that magnetic field, which creates a current just by the voodoo that is electromagnetism, right? When a magnetic field is disturbed, a current and a voltage and current are obviously interrelated, uh, just creates that current, which then we can send through some wires into uh, a speaker system or tape machine, whatever we want, right? So, or the other way would be with a condenser microphone, where instead of electromagnetic induction, it's varying the capacitance, right? Because a condenser microphone has that kind of round diaphragm in the middle, where one side of it is very thin and vibrates, changing the distance between that and the fixed plate in the back of it, which acts as a capacitor that changes its capacitance, which then creates an electric current and a voltage, right? Well, speakers work in really the exact opposite way. So, whereas a microphone or our ears, for that matter, take changing sound pressures and convert them into electric signals, a speaker is taking an electric signal and converting it into a different form of energy, which is then uh, uh, pressure waves, right? So there would be a lead wire, coming in to this speaker, which, if it's playing back from a recording, is playing a continuous audio signal, which means the voltage in that signal is continuously changing. As it passes through this coil of wire, it the current going through this wire disrupts the magnetic field that is being generated by this magnet behind the speakers. So I don't know if you've ever looked at the back of a speaker or taken one apart, but speakers have a big fixed magnet on the back of them. Might not necessarily be big, but it's usually a powerful magnet anyway. So as this, so the magnet is generating a magnetic field that is fixed, right? And as the voltage and current is going through this coil of wire, that is disrupting the magnetic field that is existing there. Because of that disruption, it actually causes this magnet to move. And because this magnet is fixed to the speaker cone, it then causes the speaker to move back and forth, proportional to the change in voltage of the audio signal come through. So it's moving this speaker, which is then producing actual mechanical waves that are pushing air molecules that then would hit our ears and repeating this cycle from before, right? So a speaker is really a microphone in reverse. And so speakers are rated with like they're rated as a resistance value measured in ohms, which is all derived from Ohm's law. And we've seen this before, where voltage is equal to I times R, where I is the current and R is the resistance. So the speaker has some built-in resistance to it. And this is just the relationship between current, voltage, and resistance. And you can use some algebra to rearrange these terms. And so you can see that the current is equal to voltage divided by resistance. Resistance is equal to voltage divided by current. And so the power rating of a speaker and also an amplifier for that matter, they're measured in power, which the unit that we measure for power for systems like this is watts, right? So power is measured in watts, and that is equal to the current times the voltage. So everything is really voltage dependent. We could rearrange this equation to say that if we take V equals IR, right, which is just Ohm's law, and we replace this V with IR, that gives us P equals I squared times R. And getting a little ahead of myself here, but that's why when we talk about decibels, we can either think of it as a ratio of the power or a ratio of the intensity, because they're both voltage dependent. But it's getting a little ahead. So if we look at just some basic little circuit, your battery is your voltage source. In this case, a light bulb would be your resistive component, and the current going through this wire would be I. And so all of the voltage, if this is the only thing in our circuit, all of this voltage has to pass through this resistor, or in this case, the light bulb. And so even voltage is really just a ratio or a relative term. I talked a little bit about balanced electronic components having a ground or a reference point. That's just another way of saying that it really, in a particular circuit, as long as it has the voltage difference that's required to power that circuit, it doesn't matter what the common or the ground reference point is, as long as this side is increased by the amount needed versus the ground. So in this case, this is just an unbalanced circuit. So if this is, say, a 9-volt battery, this side of the circuit would be 9 volts. All 9 volts drop across this light bulb, and then we have 0 volts coming back in here. And then it goes back through the battery, or the current continues through the battery, and we get 9 volts coming out here over and over and over. Same thing with a speaker and an amplifier. It's just an electric circuit that on one end is coming out of the amp. The current is going through here, and all that voltage is being passed across the speaker and going back into the amplifier, or the current then going back into the amplifier. So it's still just a closed circuit, right? And like I said before, power is measured in watts, and it's the current times the voltage. Current is measured in amperes, which is usually abbreviated in just amps, not to be confused with amp here being short for amplifier. Amperes are a unit of measure for current, which is often just called an amp, like 1 amp or 5 amps. And then V is obviously voltage. So now, one thing with speakers and amplifiers, if you've got just a pair of computer speakers, say that's what you're listening to this on, your computer speakers have an internal amplifier inside of them, right? You don't have to plug them into an extra piece of gear. They're plugged into the wall, right? Because they still need some voltage, but that voltage is powering the amplifier inside of your speakers. Just like in the studio, the smaller speakers, those focals, those smaller speakers have their own internal amplifier. So they get the power they need from the wall. The wall, or that power is supplying the amplifier inside those speakers, creating this circuit. The big speakers in the studio, those PMCs, those have an outboard amplifier, which is in the room next door to the studio. And you want to have a what am I trying to say? There's a correlation between how big of an amplifier you need versus how much power your speakers can handle. And so let's say your speakers can handle up to 100 watts. You would want an amplifier capable of handling many times that, at least a few times that. So if you've got a 100 watt speaker, or a speaker that can handle 1000 watts, you would want an amp that can produce at least 300 watts. And the reason for that is, again, the signal coming into this amplifier is coming from a Pro Tools or a tape machine or whatever. And that signal is a continuously changing voltage, right? And so you might have certain peaks, and those peaks are just momentary, real almost instantaneous peaks in voltage. It's not continuously at the maximum voltage being amplified, right? So there's a measurement called the root mean square, which is like an average. It's not exactly an average, but it's kind of, you can think of it as an average, where most of the signal is operating at some average level. But momentarily, little spikes here and there, there's going to be significantly higher voltages. And so your amp needs to be able to handle that. And so for that reason, you want an amp that can handle many times more than what your speaker can. Because if this speaker is pulling 100 watts of power from this amplifier, if the amplifier is only rated for 100 watts, this amplifier is humming at 100% capacity the whole time. And over time, and probably not over too much time really, this amplifier is going to overheat and components are going to start to fry up, and eventually you're going to blow up your amp. So you want the amp rated for many times, at least probably 3 times what the speaker you're driving can handle. And let's see, is that kind of, I guess that's kind of it about that. Let me show you a little, let's see. So here was an amp I was looking at. This is a 2-channel amp that each channel can supply 1200 watts, right? But you wouldn't want to run this amp at 1200 watts on 2 channels continuously. Eventually you're going to blow this amp up, and you don't want to spend $1,000 and then immediately blow up your amplifier, right? So it doesn't have, just because it can produce 1200 watts of power, doesn't mean you want to use 1200 watts of power continuously. Actually, this one in particular says 1200 watts continuous per channel. So, okay, so let me walk that back. This one is actually rated for 1200 watts continuous per channel. So that means that this amp probably can handle many, many times that 1200 watts at instantaneous moments. Otherwise, if it was a 1200 watt amp, like maximum, you could not run it continuously at that power rating. So if this is saying 1200 watts continuous, it means that for momentary spikes in voltage, it can handle significantly more than that. And I don't know if you've ever, if you're a guitar player, you've definitely seen on like a speaker cabinet, you can typically adjust the resistance value, the ohms, from typically between 4 to 8. Those are kind of common values for a speaker cabinet, and that's really, really low. Like 4 or 8 ohms, that's super, super low. The reason for that, the purpose for it being wired that way is, again, if we look at Ohm's law, if we have a continuous voltage, right, say the voltage doesn't change, but we have a really low resistance value, that's going to result in a really high current. So if our amp is producing a certain amount of volts and we're going across a really low resistive value, there's a lot of current coming through this circuit just by the relationship of Ohm's law. If you adjust any one of these terms, the other ones will be affected, right? So if our current goes way up, right, because we have a low resistive value, current goes up, and so power is going to go way up. So these speakers can handle a significant amount of power because the resistive value of them is so low. And again, that's why amps have to generate so much power, because the speakers can handle it. And if the speakers can handle it, you want an amp that can handle significantly more than that. Again, because you don't want to tax this amp for long periods of time, because it'll just start to burn out. And the same goes for your speakers. I mean, if you've ever had your speakers blow out in your car or your stereo or wherever, there's typically one of two things happening: that you're driving this speaker too much, you're cranking it too much for too long of a period of time. So there's a lot of power coming from this amplifier going across this speaker, and you can literally, over time, because there's so much air pressure being pushed through this speaker cone, you're either going to get very, very minuscule holes developed in this, because it's mostly just paper. Some of them have like a Kevlar kind of coating, but it's basically just heavy paper, and so little holes can develop over time, or the coil in here and the kind of the housing of it can start to wear down, because it's again, the speaker, the magnet is moving back and forth because of this changing magnetic field, and so that apparatus, that coil, and the housing of it can start to kind of deteriorate over time if you're driving this too much. If it's trying to if it's going kind of beyond where it's meant to go for extended periods of time. So if you're just cranking it, for hours and hours at a time, it all just wears out, and or you can, like I said, develop, they'd be tiny, but over time, tiny holes become bigger holes, more holes develop, and that's where you get that really distorted, blown speaker sound. It's really from holes developing in the speaker cone. So, going to switch gears a little bit and talk about monitoring. But before we do that, I'm just going to recap on decibels. I know we've talked about this before and where it comes from, but like, why do we use decibels? So we've talked before that 0 dB, 0 decibels, is basically the threshold of hearing. We can't hear anything that's below 0 dB. It doesn't mean that there's no change in air pressure happening below 0 dB. Pascals are a unit of pressure. And so 20 micropascals, that U with the funny tail is the abbreviation for micro. 20 micropascals is equal to what we call 0 decibels. But 20 micropascals is 0.000002 pascals. And the threshold of pain, when your ears actually start hurting because of the volume being too loud, is somewhere around 20 pascals, which is about 120 decibels. But the difference from the threshold of pain versus the threshold of hearing in pascals, it's a 10 million times difference. So this scale isn't really useful when we talk about human hearing. That's why the decibel is much more useful. We're talking about ranges from 0 to about 120, and those are just numbers that we can more easily wrap our head around. Right? Pascals are useful for when you're talking about like atmospheric pressure, like the pressure at sea level versus the pressure on the top of Mount Everest. Not so much for our hearing. And we've looked at this calculation before, where the decibel comes from. This isn't super important, but again, it's a ratio of two different measurements, right? And even though a lot of times in the audio world we don't think of where the term decibel or where the unit decibel comes from, well, it's from back in the day when early telephone transmission lines, Alexander Graham Bell invented the telephone, right? And so a unit of measure for power was needed to measure for phone transmission lines. So the bell was used to measure power across phone lines back in the day. And so a decibel, right, is 1/10 of a bell, or it takes 10 decibels to make one bell. But at least in America, we don't say decibel because it just sounds goofy, so we call it a decibel. Just like a kilometer is 1,000 meters, right? It's a kilometer, 1,000 meters, but we don't say kilometer, we say kilometer. So decibel, we just call it decibel, and the formula is 10 times the logarithm of some pressure or power that is measured versus some power that is our reference point. And a lot of times that's just abbreviated P over P0, or some initial starting condition, right? It's 10 times that ratio because, again, there's 10 decibels per 1 bell. Let's see. So, and again, the ratio is important because, I mean, nothing really makes sense without some kind of reference point, right? If I said, let's see, what's a good example? If you said how far is Chicago, I'd say, I don't know how far Chicago is, 3.5 hours, so it's probably what, 150 miles from here. Let's just call it 200 miles. Chicago's 200 miles from here. Well, that doesn't mean anything if I'm not here, right? If I'm in Denver, Chicago is some different measured distance away, right? Or, if I have $1,000, well, in reference to what? Like, what are my expenses? Are my expenses $1,000? Because if so, that doesn't really mean anything. Anyway, so everything is some kind of ratio, some kind of relationship, comparison to another unit of measure, right? We just don't necessarily think of it that way, but that's exactly what a decibel is, and that's what a lot of things are. And we need some unit of measure. Nothing makes sense without some standard unit of measure. If I say, how much money do you have, and you say 10, well, 10 what? $10, 10 pesos, 10 lira. So the decibel is just the unit of standard for sound. We'll get into more later, but sound pressure, perceived sound, there's different decibel ratings. But anyway, so it's some power, a ratio of power, right? And so sometimes you'll see dB as 10 log P over P naught. Sometimes you'll see it as 20 log I over I naught, or I reference, or your starting I, where this I is intensity, not current. And that's because we know that P equals I squared R from, it's basically a derivation of Ohm's law. Power is the same as I squared times R. And so the R's cancel out. Then we're just left with this I squared over I naught squared. And just a property of logarithms, if you have this exponent, you can bring it out here outside of the logarithm function and just multiply 10 times 2. That gives us 20. This is not super important, but you'll see both ways. You'll see decibels sometimes as 10 log P or 20 log I, and that's why. It's just a property of logarithms. But some cool things that when we're dealing with decibels is that there's some easy kind of calculations or references that we can make. An increase of 3 decibels is equivalent to double the voltage or double the sound intensity. An increase of 6 decibels is a doubling of the power or a doubling of the sound pressure, or SPL, sound pressure level. And an increase of 10 decibels is doubling the perceived loudness. And if you remember, I think I might have, yes, I do. Remember, perceived loudness is dependent on frequency. So if we're looking at different frequencies, just by the nature of how our ears work, we are much more sensitive in these kind of middle frequency ranges than we are at lower or higher frequencies. So it takes a much greater difference to hear or much greater sound pressure to hear something at 10 hertz or 15 hertz, 20 hertz. I guess this is probably 20. Yeah, this would be 20 hertz. So it takes 70 dB of sound pressure to hear 20 hertz, but it only takes about 10 dB of sound pressure to hear 200 hertz. So our perceived loudness is frequency dependent, and so it takes 10 decibels to perceive something as being twice as loud. And by more math that is not worth getting into, to double the perceived loudness or to add 10 dB to something would require a doubling of the power from your amplifier. So if your amplifier is producing 100 watts and it's, however loud that is, in order to double that, you're now having to provide 200 watts from your amplifier. Anyway, so you'll see sometimes different meterings, and they're again just reference points, different standards that things use. You'll see dBu with this under lowercase u. It's really interchangeable with dBV when we have a lowercase v. And again, it all just comes back to a voltage reference, which is 0.775 volts RMS, which again is RMS is root mean square, which is, for our intents and purposes, really an average. So it's averaging 0.775 volts, and that is what we call 0 dB on a VU meter. This is what a VU meter looks like. I'm sure you've seen one of these. A lot of audio equipment has them. And VU stands for volume unit. Again, just another standard unit of measure. So when we're at 0 dB VU, we are at 0.775 volts RMS, which is that is what 0 dB on our VU meter is this voltage rating, which is basically, 0 dB VU or 0 dB V. dB with this capital V is just based on a different standard, which is at 1 volt RMS instead of 0.775. That would also correspond to 0 dB here. And the difference between pro audio gear and consumer audio gear is just the reference point that they're using. In pro audio, 0 dB is equal to plus 4 dBu, which is what you would consider professional line level signal. And a lot of consumer gear, they call 0 dB at minus 10 dB capital V. So these are really equivalent to each other. They're just, this is what professional audio equipment is calibrated to, and this is what more consumer level audio equipment is calibrated to. And professional equipment is a balanced, right? Meaning there's all the circuitry has a hot, a cold, and a ground, or a positive, negative, and a ground, whereas consumer audio is unbalanced, so there's just a positive voltage and a ground, or a common. So, and that's why, if you've ever hooked up something like a balanced piece of gear to an unbalanced piece of gear, a lot of times it doesn't work because they're just at different references. The voltage difference among these things is usually not sufficient to where one will power the other. So and so metering, why is metering important? Well, metering is, it's really kind of your reference to what you're doing, and ultimately the goal is just to not clip. right? We don't want distortion. We don't want clipping. We don't want to go well into the red up here. So there is still a range in the red, and that's because, at 0, right? At 0 dB on our VU meter, we're only at 0.775 volts, which is plus 4 dBu. So we still have a little bit of headroom, and that's why 0 is calibrated to not quite a volt, because we still have at least 3 dB of headroom before we would hear distortion. So this is a pretty old style meter, these VU meters. You're looking to get, your signal roughly in this range, because you're seeing more of an average. You're not seeing really, it's a slow response time, meaning it literally has to move this needle. The voltage has to move this needle, and it has a lag time. So you're not seeing really clearly where things are peaking. You're just more seeing kind of that average, that RMS value. And as long as it's somewhere around 0, you know that you still have several dB of headroom, so that even if you do have a momentary peak, it's probably not enough to create distortion. Different types of meters, these Doro meters, these are they're similar to a VU meter, where you'll have your 0, and there is some kind of lag time in getting to that point, but they'll also show you these instantaneous peaks. So you don't see that on these VU meters, but on these Doro style meters, which maybe you've seen these too, this would be your average level, but then here's where your peaks get to, right? So you can see, do I even instantaneously, momentarily clip or go into these peaks, and you can adjust based on that. Some other ones that are probably much newer. I'm sure they've been around for a little while, but these are loudness unit meters. That's what the LU stands for, and FS means full scale. And what that means is 0 dB on these is an actual clip. Like, I don't know if these loudness unit full scale meters would be used in any analog sense. I think it might just be a digital type of metering, where 0 dB full scale is a digital clip. Like, you are clipping that sample or those series of samples in your audio signal. And so you can set these peak limiters, right? You can set so the true peak is saying, in this case, it's set at -1 dB. So this is saying every single sample, it'll get down to the sample level. Nothing can exceed -1 dB true peak. And then it's giving you this readout in loudness units versus dB or VU or anything like that. It's a different reference where it's going by your perceived loudness. So in this case, this is showing a range of 11 loudness units. Don't entirely know what that means, but it's these are more commonly used in mastering and especially in broadcasting, because broadcasting has very stringent regulations on how loud can something be if it's going on radio or TV. And I don't know if anybody watches normal TV anymore, but you might notice that a lot of times commercials are louder than whatever program you're watching, and there used to not be any regulation on how loud they can make it, because they know people are, right, they're getting up, it's commercial break, you get up, you go to the kitchen, whatever, so they would make the commercials louder so that even if you left the room you could hear it. And from what I understand, they're still louder, but there's a regulated amount louder that it can get. So every broadcast has to be within a certain level, and every commercial has to be within a certain level. Same thing on the radio. Anything going so radio or live TV, or not even live TV for that matter. But so these are more commonly used in those settings. Let's see. And as far as meters are useful, like so many different things we've talked about. A lot of it's personal preference, whether you like these older style VU meters or the Doral meters that are essentially just a VU meter with a peak reading on it. Some of it's personal preference, some of it's dependent on what the purposes you're using it for. Like I said, these are I wouldn't say exclusively used for broadcast and radio and TV, stuff like that. But there's a purpose for these that wouldn't necessarily be useful for say just a regular mix or for recording for that matter. So meters are there to just give you a reference point. Again, just like decibels are a reference point, your meters are giving you a visual representation of that. And depending on what you're working on, you might want to use different types of metering. In Pro Tools, you can choose what your meters are showing. So like when you see the volume meters in Pro Tools bouncing up and down, you're choosing to either see it as a VU meter or as a peaked meter, or you can choose just a straight RMS reading, which is that average, which is basically what a VU meter does already. There's probably a lot that you can choose from, especially now. I don't really mess with it much because again, it just doesn't, for the purposes I use it for, or when I'm mixing, it's not relevant to me or helpful to me, I guess, to see a different readout, but sometimes it is. And meters, though, they're still not any substitute for your ears. I mean, if you hear something clip, no matter what the meter says, something's going wrong. If it sounds good, it sounds good. And the meters are, you can kind of think of it as like if you're driving a car, you don't need your speedometer to know if you're going fast or slow. You might need your speedometer to know exactly how fast you're going, right? But just based on visual cues around you, like if you're passing a bunch of cars or if trees are flying by at a higher rate, you know how fast you're going, or you're going fast or slow. You just don't know exactly your speed. So that's kind of what the different meterings are for. It's just a visual reference guide, but as always, you want to trust your ears. And that's kind of all I've got. So if you got any questions, let me know. I'm sorry this was really weird because I'm just sitting in here talking to myself. So I hope that was helpful to some of you. Hopefully you learned something you didn't know before. And I will send a follow-up email shortly.